So the formula of electric potential is what? 1 upon 4 pi epsilon naught q upon r, where the q is the source charge for which the value of potential is to be figured out, and the r is the distance at which the potential is to be derived. Now, what if I have to take a charge q naught from this point A to point B? In that case, what will be the work done? Work done in taking a charge from A to B is, it would be same. Potential is defined as work done per unit charge, but the potential from A to B will be the VAB, which is actually difference in potential of final position and initial position. So this comes out to be VB minus VA upon what? Q naught? No, this is work done per unit charge. So it is like this only. So the formula is work done, or work done is VB minus VA, the potential difference. This is how we introduce this term, potential difference into unit charge. So due to this formula, this is the formula due to which the work done on moving a charge anywhere on an equipotential surface would be 0. Okay, equipotential surface, it is what? It is a self-explanatory sentence. Equal potential everywhere. So if this is a surface which is equipotential in nature, so every point is at same potential, right? So if I move a charge from this point to this point B by taking this path, work done will be final position potential minus potential at initial position into charge q naught, which is 0. What is any other use of electric potential or potential difference? Can we say anything more about it? Yes, we can, which is the electric potential energy. Okay, what is energy? Have we noticed that you add the term electric. Have you ever noticed that energy and work is actually same thing? Yes, we have discussed this point before also, and I'll keep on repeating this fact unless and until you guys actually memorize it, that work done and energy are one and the same thing. I'll give you a small example from +1. This is a mass m which is to be raised up to this point at height h. I am finding out work done. Work done is force into distance. Minimum force I have to apply to push or to lift this body up will be at least equal to its weight, which is what? mg. So force is mg and distance is h. mgh, this comes out to be formula for potential energy. I was sounding out work and I got the formula for energy. So work and energy are equivalent. A body has energy, it can perform some useful work. A body can do work, it can use energy, or potential energy or any other kind of energy can be stored in it. Coming back to my point of charges, I have this charge Q1, I have this charge Q2, I have this charge Q3. What will be the potential energy of the system? Okay, before going on to potential energy of the system, let's just find out the potential of this system. This is our origin. Let us say Q2 is at distance R2 from origin, Q3 is at distance R3 from origin, and Q1 is at distance R1 from origin. So what would be the total potential due to all these group of charges? Simply add, no funda of addition in vector form, because these are scalar quantities. So V1 would be K Q1 upon R1 plus K Q2 upon R2 plus K Q3 upon R3. Remember a point, if Q3 is negative here, you will be taking the sign negative here. Okay? Yes. Right now, we are not doing that. Alright? Plus dash dash dash. So if there are n terms, what would be the generalized formula for the electric potential? Summation I equal to 1 to n 1 upon 4 pi epsilon naught Qi upon Ri. the charge and their respective distance from the origin added up all together. So this will give you the total formula of the total potential for a system of charge. Now I want to find out the potential energy formula, the work done in bringing all these points together. See how we can do it. Consider that in my whole system, suppose this system is this whiteboard. Suppose this whole system consists of just one charge. Okay. I'll make it more simpler for you to understand. Suppose these are 3 points. I have a charge Q1 which is at infinite distance from A. Okay. What will be my work done in bringing this charge from infinity to this point, considering that there is no other charge in the system? Exactly, the work done would be 0. So I have brought this Q1 from infinity to this point. My Q1 is in here now. Okay. Now I had another charge Q2. Wait, before moving on to Q2, work done in bringing Q1 from infinity to this point was, let us write it like W1, which will be equal to 0. I have another charge Q2 which is again at infinite distance from point B. I am bringing this charge from infinity to this point B. Work done will be, now we have a charge already present in the system. So work done, what is work done? Work done per unit charge is potential, right? So work done is potential into charge. To remember, this potential is due to the source charge, and this charge is always the charge which is moving. Alright. So by this source and moving, you would remember in formula which one to use where. So right now I have this charge Q2 moving to point B. So the formula for work done in second case would be, what is the potential at point B? It is due to charge 1, right? So it is V1 into which charge was moved? Q2. Because work done is always V into Q. Already present potential at this point was due to this charge Q1. Make it bigger one. Alright, charge is already there. And now Q2 is here. So there was an existing potential which was V1 and the charge was Q2. Alright. Let us also consider a distance between them is R12. Okay. Now, what if this is done, this is right. You want to further elaborate it, you can write it like 1 upon 4 pi epsilon naught. V1 is due to Q1, that means Q1 upon distance R12 into Q2. Instead of writing it like this, I would be rather writing it like Q1 Q2 upon R12, one and the same thing. Now I have another charge which is here, Q3, again at infinite distance from point C. I am bringing this charge from infinity to C. The work done, marking it as W3, the work done would be what? Potential into charge, potential into charge. The charge here would be the charge which is moving, right? So potential into charge, whatever potential is already here at this point, into Q3, which is to be moved from here to there. What are the potentials present already at this point? There is a charge 1, there is a charge 2. That means there are potential due to these two charges. So if I brought Q3 here, the total potential would be V1 plus V2. V1 was due to this charge, V2 was due to this charge. Work done would be V1 plus V2 into Q3. Alright. R13, distance between, this is R, what? 2, 3. Is it clear up to this point? Then I want to add more charges into, I want to bring more charges into system. I want to bring Q4, I want to bring Q5. So instead of doing that lengthier process, let's just find the total work done in this process and we will generalize the equation. So to total work done in bringing these three charges would be W1 plus W2 plus W3, right? See what happens to the equation. I am not writing total work done. What I am writing is therefore total potential energy stored in the system is equal to what? Total work done, which is equal to W1 plus W2 plus W3. What was W1? 0 plus 1 upon 4 pi epsilon naught Q1 Q2 upon R12 plus what is W3? If you want to open it up right here, this is 1 upon 4 pi epsilon naught Q1 upon V1. The V1 is due to this charge, so R13 plus 1 upon 4 pi epsilon naught QV2. V2 is due to this charge, Q2 upon R23 whole into Q3. So instead of writing this, instead of writing it like this outside the bracket, I am removing the bracket, Q3 here, okay, and Q3 here. Sorted? So the equation becomes this plus this equation, 1 upon 4 pi epsilon naught. I will not be using K, and I don't want you guys to also not to use K, because when you use K, you start writing, you forget to mention epsilon m, which is sometimes required and very important in numericals. Q2, Q3 upon Q23, this term is taken, this term is taken, last term, plus 1 upon 4 pi epsilon naught Q1, Q2, Q1, Q3 upon R13. You have taken this term as well. This is our general formula for total potential energy of the system, U. This is the value of U, okay. If I have to generalize this equation, see this point, 1 2 1 2, 2 3 2 3, 1 3 1 3. That means if I have to generalize this equation, what will I write? Instead of using I'll be also using J. So using this formula, U will be equal to summation I equal to 1 to n summation J equals to 1 to n 1 upon 4 pi epsilon naught Qi Qj upon Rij, with two conditions. Number one, there is not a single term where this is 1 1 and R11. Obviously it won't be, because R11 is, there is no distance from one point to the same point. So I have to write a condition that I is not equal to J. This partially completes the formula, not completely. What have I left in this formula? Can you figure out? Think for a while. What is left in the system? See, okay, consider this example. There are three charges. That means n equals to, n is equal to 3, right? If I have to write the same equation, if I have to open up this equation up for I equal to 1 to 3 and j equal to 1 to 3, my equations would be U, I would start with I equal to 1. For I equal to 1, what will be the value of j? 2 and 3 both, right? Then I'll start with, there will be basically two terms, one plus another term. Then when I is equal to 2, because I is equal to 1, j cannot be equal to 1, this condition has to be followed. Then when I equal to 2, j has to be equal to what? 1 and 3. So two more terms. Plus when I equal to 3, j equal to 1 and 2. So this gives us two more terms. Total there are 6 terms, and actually for 3 charges we have just derived that we are left with only 3 terms. So where are these 3 terms extra coming from? This is just due to the formulation of summation sign, that I12, the equation the values Q12 upon R12 and then Q21 upon R21, basically one particular part will get repeated. So having 6 terms, out of which these 3 and these 3 are equal in value, so to remove that factor we will put half in front of it. So this completes the formula for potential energy for system of charge.